Hi, welcome back. In this virtual chemistry lab, we will be investigating or trying to simulate isotopes and how different versions of isotopes contribute to the average atomic mass that we see for elements on the periodic table. So I don't have the kind of equipment to actually precisely measure the total volume and mass of pure samples of matter, and I also don't have any pure samples of matter just lying around, and they would have to be in perfect shapes, perfect spheres, perfect cubes, or cylinders for that to work in any practical way. So instead, I use pennies for this lab. Now, this virtual lab will be very different. I will basically be doing all the procedures for you, but I still think that we can learn quite a bit about isotopes and how we can compare the pennies to isotopes in this lab. So I'm going to give you the background of all the information for this lab to set up. This is a lab that I really do in my chemistry class. So I'm just going to go over the document. I will attach in the description to this video a copy of the virtual version of the lab document that goes with this, if you want to check it out. So in 1982, the United States government, they changed the way that they make pennies. Before 1982, pennies were 95% copper and 5% tin. Now they're 97.5% zinc, and they're copper coated, and it's just 2.5% copper. And they did this to save money. It was cheaper to do this. So the pennies are the exact same size and dimension, but although zinc is a heavier element than copper, it's one spot ahead of it on the periodic table. Zinc is less dense. It's way less dense than copper is. The average atomic mass for zinc is 65.39 AMUs, but its density is only 7.133 grams per centimeter cubed. The average atomic mass of copper is less than zinc. It's 63.546 AMUs, but its density is way higher. It's 8.96 grams per centimeter cubed. So copper is more than 20% more denser than zinc. So this means if you had two equal sized, let's just say 1 centimeter cubes of copper and one of zinc, the copper cube would be heavier because there is more matter. There are more atoms of copper inside of that cube than there are atoms of zinc inside of the other one. And so consequently, old pennies are heavier than new pennies because they have more mass. Now, mass and weight are different things. Weight changes depending on where you are. You are weightless in outer space. You would weigh less on the moon than you do here on Earth. But your mass does not change. Mass is the amount of material you're made of. It's literally the number of atoms that you are composed of. So because copper is more dense, all that means is the sheer number of atoms inside of a penny made of copper is much greater than the number of atoms inside a penny made out of zinc. Exact same size, but different materials and different numbers of total atoms of those materials. So that's why, even though the zinc atom is bigger and heavier, the atoms are more spread out, its density is less, so the mass of the mass of the new penny made of zinc is less than that of the old pennies. So for this lab, in our case, the pennies represent atomic nuclei, and the mass of the two different pennies represents their isotopes. So instead of thinking of the pennies as being made of copper or zinc, instead let's imagine that these two kinds of pennies are two different isotopes of the same element. Let's just call it Pennium or Pennium or whatever. So knowing what you know about isotopes, I want you to try to think, how is using these two different pennies very similar to isotopes, but then also how is it weighed different? So I'll include some pictures right here. This is the general setup for my lab. So I have about 1,000 or so pennies, which is $10 worth of pennies. And they weren't sorted, so I had to sort through and find all of the pennies I could that were from before 1982. And there were only 67 of them, so it was kind of a needle in a haystack thing. Then I just gathered 200. I figured 200 was a good enough number. 200 of the modern pennies. So according to my calculations, the 200 modern pennies, they have a combined mass of 507.1 grams. So you need to write this number down somewhere or just keep it in mind. The total mass of all of the older pennies was 205.8 grams, but there were only 67 of those pennies. So keep those numbers in mind. So what we can do is we can take these numbers and figure out, well, what is the average mass of the pennies, these real world pennies that I have. Now, according to the US Mint, the mass of a brand new penny should be exactly 2.5 grams. Well, let's just do the math right here. And it turns out that my pennies, the pennies I have, are just a tiny bit heavier on average than what the standard penny should be. We'll talk about why that might be here in a little bit. The old pennies are supposed to weigh exactly 3.1 grams. So let's take the total mass of the old pennies divided by the number of old pennies I have. And it turns out that we have lost a little bit of mass with these older pennies. So on average, each penny weighs, it's really small, but they weigh a tiny bit less than they should have. Now what I did was I took my cell phone and I have I don't have it with me here, but I have a fancy little magnifier, and I took some really close-up pictures of some of the old and new pennies. Now with the new pennies, to make this interesting, because we're gonna have percent error. Our numbers are gonna be slightly off. So I tried to find some really dirty pennies, right? And all of that extra corrosion, oxidation, there's dead skin, and I mean, who knows what is on these pennies. That adds to them. So here you can see a close-up view of one of the newer pennies, sort of a cleaner one, and then I have pictures of some really, really dirty ones on there too. Now with the old pennies, they actually kind of all looked the same. Here's the oldest one I could find, a 1950s penny. That was the oldest one I had. And then here's another one of the pennies. They all kind of look the same. They're just kind of dark. None of them were particularly dirty, so they didn't really accumulate too much. It turns out that they actually somehow lost a little bit of mass. Now what is that from? They get bumped and nicked and worn down, and they get chemically weathered, so milligram by milligram, I suppose tiny amounts of them can be lost over, I mean, one of these pennies is, it's almost 70 years old, actually. Well, closer to 60 years old. So the fact that our numbers don't match the hypothetical or the theoretical weight or theoretical mass of a penny, that's totally fine, because when we do experiments in science, we have what's called the accepted value and the experimental value. So the accepted value is, assuming everything is totally perfect, this is what we should get. And that's where 2.5 grams or 3.1 grams for the older pennies, that's where that value comes from. That's the accepted value. The experimental value is what we find in the real world. So we want to know like what our percent error between those two things is. How close to the real world answer are we? In this case, we are actually really close to the normal value, which sort of makes sense. Now, we can also take the volume of these pennies and calculate their density. And we want to do this because the old pennies are, close enough to 100% copper. And we know what the density of copper is, or at least we can look it up online. And the newer pennies are close enough to 100% zinc. And again, we can look up the density of zinc. So how does the density of these pennies compare to the actual experimental density of these pennies? How does that compare to the accepted density of them? So to figure this out, we do the volume. And you'll have to look this up too, but actually I already did it for you. A penny has a diameter of 1.905 centimeters, and it has a height, a thickness of just 0.152 centimeters. So knowing this, we can calculate the volume for both of our sets of pennies. The volume for a cylinder is pi r squared times height. Now we have to change our diameter to a radius. So I will just do that digitally here. And that gives us the volume of just one penny, but we have many of them. So let's find the total volume for our 200 modern pennies. There it is. Now let's take the total volume for the older pennies, and there are fewer of them, only 67, so the overall volume is going to be smaller. And there it is. Now to find density, we take mass divided by volume. So we're going to take the total mass. We always want to use the largest numbers we can to try to be as accurate as possible. So we're going to take the total mass of all of our, let's start with the modern pennies. Let's take the total mass of the modern pennies and divide that by the total volume. Density equals mass divided by volume, and voila. Here is the total density of our modern pennies, and it is only 5.85 grams per centimeter cubed. Now you'll remember from earlier, zinc, which these pennies are almost 100% zinc, zinc has a density of 7.133 grams per centimeter cubed. This is way off. Our mass, our average mass for our pennies was really, really close, but the total density is way off. Let's look at the old pennies and see what we have. So we have, let's take the total mass of our old pennies. There it is. Let's divide that by the total volume of the old pennies, and that comes out to 7.09 grams per centimeter cubed. These pennies are made almost entirely out of copper, but copper has a density of 8.96 grams per centimeter cubed. So our density values are way off. Now, there's a particular reason for this, and it has to do with, well, it's just the nature of money. Now, I'm not going to give you the answer to this one. Think of the penny. Actually, let's put the picture of the penny up here. Remember, volume is radius squared times pi times height. Now, we have a penny. We know how wide they are. We know how thick they are. But because it's a coin, there's certain things about it that are different. Again, I'm not going to give it away, but there is something which you should be able to see in this picture that is accounting for the fact that our density is way lower than it should be. So let's go back to mass. We have the overall average mass of both of these pennies. So on the periodic table, when you look at an element, its atomic number is always a whole number. Its atomic mass is never a whole number, except for a very few number of elements. I think all of them are man-made elements. So the reason it's not a whole number is because it's an average of all the isotopes, and it's pretty much impossible to get a whole number that way. So if we take our pennies and we take their mass, these are isotopes of pennies, remember. So we have the modern penny, which is a little bit lighter, and then the old penny, which is a different isotope that is a little bit heavier. So if we take the total mass of both pennies and then divide that by 267, because that's how many total pennies there are, this is the overall average mass of our pennies. So the last thing for you to think about with this lab is, how is that figure, the way this number, the average, how that relates to the mass of the new penny and the old penny, how is that similar to the different isotopes of elements, and how that relates to the average atomic mass that we find on the periodic table. So I hope you enjoyed, I hope you learned something, and thank you for watching.